Let me give you a little help here for calculating the power that has to go into the motor. So the idea here, again, is we're using the law of conservation of energy formula. We're comparing two locations. The loading zone, we'll call it A, and the top of the hill, we'll call it B. And so the formula that we use for conservation of energy is this formula right here. Should be familiar to you. And, if you start thinking about this, you should be able to calculate the potential energy in the loading zone. It's at ground level. You should be able to figure out the kinetic energy in the loading zone because it's at rest. People don't run and jump onto the motorcycle and the roller coaster, I meant to say. And then you also should be able to figure out the potential energy at B, the top of the hill, because you made up the height of the top of the hill. And of course, I've said let's make the kinetic energy, the velocity at the top of the hill, 0. So the only thing really left for this equation to give you is the work done by the external force, and that's the motor. And what the motor is doing, the work that is being done by the motor is what's generating this potential energy right here. So then when you go to calculate power, remember that power is just, you can do it as work over time. You can do it as how much energy has been transferred over time. But basically, power is work or power is energy divided by time. Now, there's one additional issue here, and that is that I said that the motor has an efficiency of 75%. So and that's where an energy diagram comes into this. So what that means is, okay, maybe you calculated how much energy the motor put out, how much energy the motor created. And this is the output over here. The energy out is over here. But how much energy had to go into the motor to make that happen? Well, at 75% efficiency, only 75% of the energy that goes in comes out as something useful. The rest of it becomes heat. So what is this energy that we put into it? Well, that's the electrical energy. That's what we're trying to figure out. How much electrical energy do you have to put into this motor? You're plugging in the motor, plugging it into a wall. So how much electrical energy did you have to put into this motor in order to get the electrical energy out? And I'm using the word energy here, but you can do this with power too. How much electrical power had to go into the motor in order to get the power that you got out of the motor? So hopefully that gives you enough of a hint that you should be able to put those, I'm hoping you'll be able to put those numbers together and figure out how to do that. Now, the other issue is the heat. So, and by the way, some people were confused. I have this word heat here. And it's true, the motor heats up. And that's something that in the energy diagram, I want you to figure out. How much does the motor heat up? But the last question, which is the heat dissipated by the brakes, that's a completely different question altogether. So again, if you think about your roller coaster, now we're thinking about the end of the roller coaster journey. Whatever your roller coaster looks like, eventually at the very end, the roller coaster is going to come to a stop. And again, we're going to be using this equation, U at A plus K at A plus W external equals U at B plus K at B. So let's just call this B at the very, very end of the ride. And so you know what potential energy it has there because it stops at ground level and it's stopped. So you should know its kinetic energy there as well. So those things you should be able to figure out. Now, what are we going to put in here? Well, you want to choose a spot where it had a bunch of energy. And honestly, that could be at the top of your crest, that could be at the top of your loop, that could be at the bottom of the valley, that could be at the initial hill, because it actually has exactly the same amount of energy at all four of those spots. So just pick any one of those spots for a location where you know its initial amount of energy. You should know the potential energy at that spot and the kinetic energy at that spot. So the only unknown is the work done by the external force. And here, the external force is the brakes that bring this thing to a stop. The brakes do work as they bring it to a stop. And they do work by creating friction. And friction always creates heat. So basically, when I'm asking you to figure out the heat dissipated by the brakes, it's really equivalent to how much work the brakes had to do. So hopefully that makes sense, and you'll be able to not be frustrated by that. All right, good luck.